It's pretty interesting in that regard. So when hyperventilating, a person breathes in and out very rapidly. A spirogram is a machine that draws a graph of volume of air in a person's lungs as a function of time. Okay? So the graph is a spirograph. I have like printouts of spirographs from myself, and they say they're normal, but they don't look anything like a cosine graph or a sine graph or anything like that. So, we're kind of suspending our disbelief a little bit here to say that it could be perfectly modeled by a nice, neat cosine graph. Right? But we could say in general that it could be approximated by a cosine graph. So there's going to be some minor variations all over the place, but in general, it would follow this relationship. So, or it could be a sine graph, depending on where in the process you're starting the reading. Because here you're starting off with a volume of air at three somethings liters of air initially. All right, so that's saying that the person's already started basically with a full lung full of air. Right, as opposed to a sine graph where maybe they're starting with no air in their lungs, right, or at least as close as you can get to no air in their lungs. All right, so here's our volume function, and what we need to do is create a graph of this, and then also do some things involving the derivative. So the graph part that's the fun part. All right, you can do it on your calculator, but again, you can't always operate under the assumption that a calculator is going to be available to you, as you know. So let's review some facts related to graphing a cosine function. First, I'm going to rewrite it as negative 0.05 cosine 200 pi t. I'll put a plus 0 in there. Plus 3. I just want to make it match up with the general form of a cosine graph as much as possible. Because in general, it would be a cosine bx plus c plus d. All right, so good old algebra 2 again. All right, so we know that from this that we have an amplitude of negative 0.05. All right, so it looks like we're starting off with a little bit less than full capacity. Then a b value the b value would be 200 pi. All right, from that we can get the period. Period of a trig function formula? That's close to the phase shift formula. That would be negative c over b, 2 pi over b. All right, so in this case, it would be 2 pi over 200 pi, which would be 1/100th of a minute. All right, so the units for the amplitude would be liters. That's a measure of y. And the units for the period would be minutes. All right, the d value in a trig function is your vertical shift. All right, so that's our VT, vertical translation. All right, so we have everything we need to construct a graph by hand. Everything that's important in a trig function is going to happen in quarter period increments. So it really doesn't matter what the period is. That's just going to be the end point of your cosine wave. Okay, and so then we'll just divide that into quarters. Once we do that, then we'll have all the locations of the special points along the graph. In terms of the y values, I do want to get a sense of how this graph relates to 0 in all cases. So I want to have a y-axis and I want to have an x-axis. We don't want to just arbitrarily identify the location of 3 and then go from there. That would make things look probably too nice, and nice is really not what we're looking for here. We're looking for something that models what's actually happening. All right, so this is talking about somebody who's breathing very fast. All right, so the change in volume should be happening very quickly, but also the amount of volume contained in the lungs should be, or at least the change in volume should be very small. All right, so the rapid, shallow breathing is what we're looking for here. All right, so a graph that models that would be important for us. I'm still getting used to it. Line draw tool. Line draw. Undo. I don't know why it just doesn't stay on the most recent function. There's got to be a setting for that. If you know the setting, then please put it in the comments section down below. And also hit that thumbs up icon, support the channel, and smash that bell to receive notifications for future videos.
I was watching the videos the other day. They're so funny because sometimes for 5 minutes we just talk about cones.
Yeah.
And then it's just
I would have stopped being a teacher 15 years ago if I couldn't do that. But if it was, I love math, don't get me wrong, I love it. Probably too much, but I don't love it enough to just talk about it or drone on for 40 minutes straight every single day. I just can't do it. There has to be a mixture of Star Wars, Avengers, cooking, and we haven't talked about cooking in a while. Chili, yeah. Hungarian goulash is on the menu for later in the year. We've talked about that.
Can you go over how disappointing it was they didn't actually play Sweet Victory at the Super Bowl halftime?
They didn't what?
They were gonna. So there was a thing where they were gonna play Sweet Victory, the song from SpongeBob, where they in one episode of SpongeBob they played Sweet Victory at some halftime show, and so.
The Bubble Bowl. Yeah.
And they were gonna do it actually during the halftime show, and then they played the first 10 seconds of it, and then it cut into Sicko Mode by Travis Scott, and he came out. It was really frustrating.
That whole experience yesterday was frustrating because one, you can't play moves like Jagger and then not have Jagger come out. So,
or Christina.
And then he took off shirt and was like, California.
Yeah. That's great, we're in Atlanta, but whatever. Also, even more heartbreaking, and this is probably the most important thing that anybody could even remotely consider, is that they were supposed to air 3 separate Star Wars trailers during the Super Bowl for the upcoming Episode 9. And unless they did, and I missed it,
I'm pretty sure
they did not. It was supposed to be one trailer broken up into 3 parts for the 3 different perspectives. It was supposed to be one from Rey's perspective, one from the Resistance, Poe, Finn, and all their perspective, and then one from Kylo Ren's perspective. That would have been great. I watched the whole Super Bowl.
Overall, just disappointed.
The game sucked.
The game was really boring.
So, it didn't have to be a 70-63 shootout.
Yeah.
Maybe more than one touchdown would have been nice.
Yeah.
All right, anyway. So there's your 5 minutes, by the way. Oh, that's for period 1. I am going to print up that picture and blow it up and make it a nice sign to have, and it's going to say period 1, get out.
I can hear snakes.
Or
Just
the beard guy.
right off the astronomy tower. Boom.
on that
All right, so the period's 1 over 100. So I just want to go out in terms of a scale for x, some multiple of 4 units. So, pick your favorite multiple of 4, I guess. I'll go to 16. So 1, 2, 3, meh. 1, 2, 3, meh. So that would be one full period, 1/100th of a minute. This is our t-axis. I'll just kind of chuck it in there. Oh, actually, you know what? I drew that line, so I can erase some of it. I have the power to do that. Apparently, I don't have the power to do that. So I'll have to just live with it. So, beep. T-axis. Und the V-axis. All right. So I want to break that up into quarter unit increments. So I'll chop 1/100th in half. And I'll get what? Czech Republic is incorrect. 1/200.
How do you say it?
Oh no, I was looking for 1/200th. It's Czech Republic. I mean, that's the place.
Isn't it Czechia now?
Is it?
It's just Czechia.
Oh, they changed it up. I better Czechia myself. 1/400th. So it's a quarter, half, 3/4, so 3/400ths, and then 1/100th. All right. Eventually, they're going to ask things like maxes and mins and stuff like that. And since we know all the important stuff in a trig graph happens at those quarter unit increments, provided there is no phase shift, and there is none in this case because there's no C value, we're in pretty good shape. All right. So we're starting off 0.05 units below 3. All right. Because instead of being, or at least having a midline at the x-axis, we're going to have a new midline at y=3. So I'm going to start 0.05 below 3. I'm just going to get in real close there. Extreme close-up. I'm just going to ballpark it, obviously, because that's nowhere near where 0.05 would be. Then we hit the midline at the quarter-way point. We hit the maximum at the halfway point, just a smidge above the midline. Back to the midline at the 3/4 point, and then down to the minimum at the end point. So right about meh. Very shallow cosine graph. And when I zoom out even further, it looks less and less like a cosine graph. Yeah, it looks like how I normally draw a line. Exactly. All right, on the calculator.
What is confusing? What's with like
Ponder away. All right, so but while you're doing that, I'm going to put the equation into my calculator. I'm going to put the period in as my x max, so 0 to 1/100th. This is a little calculator skill that we don't always use, but it's very useful because it'll give you the range provided you give the domain. Right? And then from there, you tweak it as needed because, again, I want to see the x-axis because I want to get a true sense of what's really going on physically here. If I didn't have the x-axis and I just plotted 3 at some arbitrary location and then I just made up a scale for 0.05 to make it look like a nice sweeping cosine graph, that wouldn't really illustrate what's happening in this sense. Right? So this person is breathing in and out very fast, so the volume of air, they're not expelling all of the air, they're not taking in basically a full load of air. All right, so I'm going to hit zoom fit on the y min or y max, so zoom 0, and that's going to give us what the perfect window would be based on that domain to show the lowest and highest parts of the graph, which is great. But again, I want to see the x-axis, so change my window so that the lower bound for y would be 0, and now you can see that it's doing a nice job of really getting across the idea that it's not a very significant change in volume.
Okay, first cosine graph. Well, I got negative cosine graph.
Right.
So how do you know that the change on the y's, like basically?
Those values?
Yeah. How do you know they were small?
Because the amplitude is 0.05. So that means that the most deviation you have from your midline would be 0.05 units.
Okay, so the 200 pi t does not factor in.
That just impacts the horizontal distance necessary to complete the wave. So what that's telling us is that in a 2 pi period, we would actually get 628-ish full cosine waves, right? Because that's what the frequency would be, all right? So that's telling us that, yeah, in about 6.28 seconds, we're looking at about 628 inhale exhales, all right? So that, if that doesn't illustrate the idea that the person is breathing in and out very rapidly, I don't know what that does, right? Over 600 full inhale exhale in 6.28 minutes. Sorry, I think I said seconds. All right, but that's still a lot. All right. So rapid breathing. If you've ever seen, if you've ever hyperventilated, you know exactly what this is. But if not, you've probably seen it in a TV show or a movie or something like that, where the person has the paper bag, and they breathe in and out because they're low on carbon dioxide. They're over oxygenated, and because of that, they're hyperventilating, and they just need to slow down their respiration, so they introduce more carbon dioxide to slow the process. All right, so it's basically like they're killing themselves on purpose, very slow, in a very minuscule way. Yeah, but you know how like a vaccine, you're introducing a very small amount of whatever it is that you're trying to protect yourself from. That's the same idea. Like with hyperventilating, you're introducing a very small amount of the thing that would kill you, right? So like that's generally what's going on there, all right? In order to slow down that respiration. All right, rate of flow in air, of air in liters per minute, and then we'll sketch a graph. But let's worry about the function first. So V equals negative 0.05 cosinus 200 pi t plus 3. All right, so dv dt, or v prime, either way, doesn't matter. What would our derivative be? Point zero. Sine 200 pi t times, what did you say? Times 200 pi. All right, we can clean that up a little bit. All right, what's 0.05 times 200? 10. So 10 pi sine 200 pi t. All right, so in terms of the sketch, the x-axis can remain the same because our b value didn't change. So our period's not going to change. So that's news. All right, yeah, so the reason why I have to erase, if you didn't pick up on it, is because we have an amplitude of 10 pi. But no vertical translation. Because there's no vertical translation, this graph should be centered around the x-axis. And you don't have to put it directly in the middle, but you definitely need to leave some room below it in order to create some graph. And so that was my bad. I put 1 in 400, 1 in 100. I meant 1 in 400. That's a 4. It doesn't really look like it though. 3 in 400, and 1 in 100.
Is that 1/400?
1/400, yeah. Try to correct on the fly, but it doesn't really look like much. Let me try. Bring it in a smidge. There we go. All right. Now the good news about this graph is we can put the amplitude of 10 pi wherever we want because there's no movement from there. So you could actually figure out what 10 pi is around, obviously 3.14 times 10, so 31.4-ish, and then scale from there. But I don't think that's even necessary. So I'll go up like 3 boxes just because 3 felt like it would give a nice looking picture. Maybe 4 feels better, I don't know. So this is our V prime graph. And so a sine graph starts at, a positive sine graph anyway, starts at the midline, hits the maximum at the quarter wave point, then the midline again, then the minimum at the 3/4 wave point, and then back to the midline. So, all right, so more of a classic looking sine wave, all right, but again, only because we're not given a scale and we're able to decide what it would look like. A little bit easier to relate to values or units that are not rates, but once you incorporate a rate, it's like, okay, so the volume is changing at a rate of 10 pi sine 200 pi t liters every minute. All right, what does that mean? Well, obviously it depends on how many minutes, but so if we're going in for 1 in 100th of a minute, we're at the moment where the rate of change is equal to 0. Right? So that's telling us that there is no change in the original function. So, what does that mean? I don't know. I'm not a doctor, but I know it means that nothing is changing, and that would have meaning to somebody. So the kind of person who does this sort of thing for a living would know exactly what that means. All right. We just know that there is no change in the function at that moment. All right. The broader implications of that are lost on someone like me, obviously. The interval where the person is breathing in, out, and then the time where the rate of flow of air is maximum when the person breathes in. Those are all the things that we're looking for. And all we have to do is mark them on the graph. So breathing in, all right, so the person is gaining air. You could look at the original graph or you could look at the derivative graph, all right? So what's happening in the derivative graph, we're just focusing on that. You're looking at specific intervals where the volume is increasing, all right? So this would correspond to the original function, also showing where the volume is increasing, all right? So focusing on the original function, anywhere where the graph is increasing from left to right, aka positive slope. I'm gonna go, no, I don't want red. Let's do I'm gonna create a custom color here. I'm gonna make a flamboyant green here. All right, so this would be the interval where the person is breathing in. All right, all we have to do is mark the graph. Oh, that's very flamboyant. So I will just. So let's do that. And then anywhere where I don't highlight it, I'll just leave that the way it is, and that would be out. All right, so person's breathing in all the way up into this moment in time, and at which point they're starting to breathe out. All right, that would correspond time-wise with the derivative graph. Let me just bring it out a little bit so we can see both. With that first arch. All right, that's where the derivative is positive. Anywhere where we're above the x-axis, the derivative is positive, so that would correspond with where the person's breathing in. All right, everywhere else would be out. Now, the last part, that's, I mean, if you don't read it carefully enough, you can get into some trouble. The time when the rate of flow of air is maximum, when the person's breathing in. The rate of flow is maximum. So it's asking us for when the derivative has a maximum point. So let me bring that up. When does the derivative and again, specifically when the person is breathing in. All right. So if you've read it carefully enough, then that would draw you specifically to this location here. That would be rate of flow is a maximum on the inhale. All right. Now, not to be confused with this point here, because one person's minimum is another person's maximum. So if you change your perspective and you're looking at it on an exhale, you could have a maximum rate of flow, but graphically it would look like a minimum point. So this would say, it would seem like this is the location where the person has a minimum rate of flow on the exhale, but it's actually the maximum rate of flow on the exhale, all right? Because the exhale part of it is what makes it negative, but if you really think about it, I mean, just start breathing. Don't breathe like this. Don't follow this model, because you'll be in the nurse's office before you realize it. Because you'll if you start trying to hyperventilate, then you will succeed in hyperventilating. So
Don't try it.
yeah, so don't try to breathe 628 times in like 6 minutes, because that's a surefire way to get yourself in trouble. But yeah, you'll feel it. It's just on a regular inhale exhale. You'll feel that the pull of air achieves a maximum on the way in, and the exhale achieves a maximum rate on the exhale. Right? So these are things that you can test out on your own. I tried doing it in class before, but it didn't work out well, because you have some coffee drinkers, you have a person who had a breakfast burrito, and people exhaling in each other's faces, especially during like flu season. Like half the class got sick, the other half was just like grossed out. So it's just not a good idea. But on your own time, like just give it a shot.
In bio, we ducked our head in water and then we measured breathing.
Same water for everyone? It's disgusting.
No, we changed the water.
Oh, okay.
We definitely did not all put our heads in the same water.
I thought it was just one person put their head in the water.
Oh, yeah, I put my head in the water.
Oh, so you were the volunteer to do it?
It's like each group has like a person who dunks their head.
Oh, gotcha. And that person volunteered to do it, obviously, because it's corporal punishment if
We weren't even at
the
that.
teacher holds your head under the water, saying it's a lab,
I could have jump rope.
And then I did the spoon.
I'd be like, well, we're gonna do this lab where we're gonna simulate like drowning, and I'm gonna dunk your head under the water. It has absolutely nothing to do with the fact that you didn't do your homework last night. I don't think that would work. So, yeah, those days are gone, I think. I don't think they're ever coming back. And that's a good thing. It's like, oh, you didn't learn math. Let me beat it into you, because that's somehow going to work. Like that. I don't understand how that was even a mentality at any point in society. But like, if I hit you harder, maybe you'll learn better. Like, I don't know. No, that's not how it works. So, anyway,